Hello, hello. Input capture. Yes. Yeah. Okay. Okay. So let me just say a few words more about this these states of charmonium and bottomonium, because I think it's instructive, because it gives you an idea that modeling even something very complicated like these systems actually can be understood because of its similarity to, let's say, positronium, which you might say is well understood. So I sent you a link yesterday of a talk which describes these things very nicely. So it gives the spectroscopic notation like this: L and J. Okay, where S of course is equal to 0 or 1, because this is the both the spins, the spin of the B and the BB bar. So it can either be 0 or it can be 1. Okay, so this is the principal quantum number, and the L over here will take the letters S, P, D, etc. And then so this can be 0 or 1, and depending on how this combines with this, you get a total J. Okay, so that is a scheme by which this thing works. So let's look at the positronium spectrum, which looks like this. So 1, 1s, 0, like this, and then there is a state 1, 3s1, like this. There's no other way, because here this means that the spin is equal to 1, L is equal to 0, so the only possibility is that this can be 1. Okay, so here the spin is 0, L is 0, so this can only be 0, it has no other choice. So that's the reason why it's like this. And then when you go up, you may get a higher state like this. So if it's a higher state, that means that the principal quantum number is larger. So 2, 1s, 0. Sorry, so that should be over here. That should be 2, 1s, 0, like this. Here you can get a 2, 3p, 1, but then you can get more rich states like this. So with 2, so then you can have a p. So it depends on what the s is. S can be either 0 or 1, and what we give is 2s plus 1. So it's a 1p1. Why should this only be 1? Because the spin is equal to 0. So here L is equal to 1, so J can only be equal to 1, and that's it. Yeah, I think it actually is a little lower than this, so let me write this here. So this is a 2, 1p1. Okay, on the other hand, you can have a 2 is the principal quantum number, p, and then you can have a 3. So if it's 3, that means that S is equal to 1. So that that 1 can combine with P, which is equal to 1, to give 0, 1, or 2. So you have 3 possibilities over here. So you can have 3P. So this is the order. So you have a 3P2, you have a 3P1, and you have a 3P0. All these 3 things are possible. So this is in positronium. Yes, sorry, you're right. So yeah, 2 is here. 2, 1, and 0. Two, 3p2. Yeah. There are other states also. Then you can go for D states, etc. So the thing is that the positronium states also follow this. Sorry, I mean this was for positronium, and so now this is for charmonium, and these things are given names. So the reason why I'm talking about this is so that you know what are the names. One is 0, and this thing is called an eta c, like this. Okay, so this is the 1s states. There are 3s states, 1p states, etc. Okay, so here is 1. So this follows the same pattern. So this is a 1, 3, S1, and this is called a psi. This is the famous J psi. Okay, So in E plus E minus collisions, you actually produce this, but you don't produce this directly, because only this has the correct quantum numbers to couple to the virtual photon, okay, in the intermediate line. So this is the famous psi that I had mentioned the other day. So there's a higher one over here, 2, 1, S, 0. So this thing is called eta C1. Okay, then this pattern is repeated, principal quantum number 3 and 3s1, and this is called a psi prime. Then you have, similar to there, you have a 2, 1p1. Nothing else is possible, okay, because the spin is 0. This is L equals 1, therefore there's no other possibility. J also has to be equal to 1. Then you can get 3 states like this. So this will be 2 is the principal quantum number. This is a p. So it's a 3, which means that S is equal to 1. And so that 1 can combine with this 1 over here to give 0, 1 or 2. So this thing has a name, chi2, 2, 3p1, chi1, I think, and 2, 3p1, chi0, like this. But what happens is that in charmonium, soon afterwards, this opens up into what is called quasi-bound states. Quasi-bound. These are the true bound states. And here the CC bar rapidly breaks up into DD bar pairs. Okay. And remember the other day we had this discussion of the OZI rule, which gave some CC bars can decay with the emission of 3 gluons like this, and we saw that it was something like this. I have forgotten how to do this. So this is OZI, whereas for the above the quasi bound states you have things like this coming from 2 gluon exchange. So this comes from 2 gluon, and this is 3 gluon, this comes from 2 gluon. So if you open the table of various charm decays, then you will see that some of them decay rather rapidly. Those which are in this quasi-bound state, they will go through the 2 gluon. So this is OZI allowed, whereas this is OZI suppressed. And this is possible above the DD bar threshold. DD bar threshold. You can see that many of these things are very nicely described in the book of Griffiths, and also this book of Prof and Company, POVH et al. So it was originally in German, so you will suddenly find some German words appearing in the figures and figure captions. So this will be called the DD bar Schwelle. In the book of Prof and Company, it's called a threshold in the other book. Okay. So a similar thing is also seen in BB bar system. So similar thing is seen in BB bar system, except that there are even more bound states. In addition, there are more bound states. And I'm going to ask you to guess for me what these quantum numbers of these bound states should be. There will definitely be a 3s1 will be there. Then there will be a 1p1. There's also a 1p1 state that is available over here. Then there is a 3p2. What else is possible? 3p2, then 3p1, then 3p0 is also possible. There is a 3p2. Sorry, this I've already written. 3p1, 3p0. Any other bound states you think should be available? What comes after P? What comes after P? D, right. So there is a 3D, so 3 like that. So there is actually a triplet, so what should be the total quantum number? What are the possibilities now? With D, L is equal to 2. If it is a 3 over here, S is equal to 1. So what are the possibilities? Correct. Yeah, so 3, 3D2, 3D1. These are all possible. And all of them have names, okay? So you can look up what are all the names, just like we had over here, this Chi2, Chi1, etc., etc. There are names like this. So what is the point of this? The point of this is not that we are just doing botany with all these systems. The point is that a simple hydrogenic type system actually has a certain spectrum, and this is also reflected in something like a heavy system like CC bar, BB bar, etc. Okay. So in a sense, of course, we don't know how exactly to get an effective non-relativistic potential, but at least the spectrum is encouraging that these systems, it's possible to understand it. So here is the Schweller for this. So this is the BB bar Schweller for this, or threshold, depending on which book you're reading. But it's also good to check the level spacing both in the charmonium and in the bottomonium system for these S states. Okay, so it's good to see. It's very interesting actually. The separation is very similar. So you should have a look. So once again, let's write a 1, 3s1, and this time I'm going to write the masters also, 3097. So this is the famous J psi. Then there is a higher one, which is a 2, 3s1, psi 1 of 3686. Then there is, so this is already, you know, quasi bound state over here, 3s1, and this is called psi of 4039, and 4, 3s1, this is psi of 415. So there are similar states over here with the same quantum numbers. So this is in CC bar and this is in BB bar. Give me a name over here that I should write. I've already mentioned the name, the BB bar resonances. What are they called? They're called the epsilon, right? So epsilon, and this is the 9460. This is the lowest one, and the next one is called epsilon prime. This is called 10023. What are these numbers, by the way? Please tell me what these numbers are. 3097, 3686. What are these? These are the masses of those resonances. In what units? MeV, right? So charm quark is about 1.5 GeV roughly. Okay. So these numbers here represent the masses of these resonances. So this thing here is telling you that there's a resonance at roughly 10 GeV, which is a rather high energy, which is BB bar. So B quark is very heavy, no? That's why the resonances are also very heavy. Then there is an epsilon double prime at 10355. And there's another one. And these level spacings are very similar. So that means that the underlying dynamics is kind of universal. It doesn't particularly care what the flavor of the quark is. Although the masses are different, the interaction does not seem to care about the mass. Okay? See, we are all accustomed to saying, oh, standard model is a very simple theory. There's only one strong coupling constant, etc. How do I know? What is the experimental proof that irrespective of what the quark is, that the gluon is going to couple with it with the same strength? So these are all the pieces of evidence that the strong interaction is universal. How do I know that the electric charge is the same for the electron as it is for the muon? We are saying that it's universal, right? So we have to test all these ideas, and there is actually only one strong coupling constant, which is known as alpha S, which couples to every quark with the same strength. So we need to keep looking for pieces of evidence, experimentally, observationally, which all support this hypothesis that the strong interaction is universal and doesn't care what the type of quark is. Okay, so this is a little bit of information about this charmonium and bottomonium systems. So the other day we discussed this lamp shift, which was very nice, and I actually went over the derivation again and again, and it's actually not that difficult, but I'm not planning to do it in class. I would like you to try to study it in by yourselves and try to make an effort. If you do not succeed, this is from the book of Mandel and Shaw. If you do not succeed in really understanding what it is, then you can come back and tell me, and then I can try to do a class. So it will take at least 20 minutes to half an hour to do that. So as we said in the previous class, we have done a lot of work with tree-level Lagrangians, various kinds. We have looked at the coupling of electrons and muons and neutrinos to each of the charged leptons to quarks. We have discussed sine squared theta w. We have discussed w mass. We have discussed the z mass, sine squared theta, gw, g prime, all these things, masses of the quarks. We have also run into Cabibbo angle, and we said that this can be generalized to three flavors. We have also discussed phenomena of the standard model such as CP violation, etc. But almost everything that we have done has been at tree level, except we drew the box diagram once for KK bar oscillation, which is of course a higher order loop diagram, but we didn't actually evaluate that diagram. So our task now is to see how the standard model actually knows about loops and the loop expansion, and how does it know about renormalization and presence of interactions, that we are forced by the rules of quantum field theory to draw diagrams in the loop expansion. At least we should be able to do it to one loop and start seeing some of the effects of taking into account loops. Okay, of course all the parameters of the standard model are parameters that enter the Lagrangian. At the level of the Lagrangian, they are just parameters which, of course, by the rules of quantum field theory, will start to appear at every vertex, irrespective of whether it's a tree-level diagram, or a one-loop diagram, or a two-loop diagram, etc., etc. So what happens to some of these parameters in the presence of loops, and what is the language that tells you how to do something about the presence of interactions and how to give meaning to these parameters? Any idea? You've done some field theory courses, right? Yeah. So there, whenever you have interactions, you may start to see divergences, and then you have to absorb those divergences into redefinition of the parameters, and that program is known as renormalization. Okay. But let us take a simple example where we start to see how it actually enters a particular process. So let us look at electron muon scattering. Just as an example, just following whatever is there in the book of Griffiths. Okay, so let us consider which at lowest order is described by diagram that you draw like this, carrying a momentum q, let us say. So here is a P1, and then here is a P3 like this, and then here there's a P2, and then there's a P4, and so this is at lowest order, and so the corresponding amplitude is given by m equals minus GE squared. This is the peculiar notation of Griffiths, instead of calling it LA, you know, just E, calls it GE, U bar P3, gamma mu, U P1. Then there's a G mu nu by Q squared. Why is there a G mu nu by Q squared? Because it's a propagator, okay? So photons propagator, G mu nu, because there's a mu here and there's a nu over here. These are free particles, external legs, so they are represented by spinors, okay? If there were internal lines, then you would have corresponding propagator for these guys also. Okay, so what comes next? How about a U bar of P4? U bar P4, then a gamma nu, and U of P2, okay? No problem. So U equals P1 minus P2. So everybody here agrees with me so far, and I'm sure you've all got A's in your quantum field theory 1 course, so you have no problem with this, right? Mr. AAGB, it's too much to say your name. You agree with this? Anything that you disagree with here, over here? Well, we'll all have to agree on something, so let's agree on this. Now, if you go to order G to the 4, how many diagrams can you have? You can have many diagrams. For instance, you can have this thing emit a photon and reabsorb, or this, or this, or this, or one of them emits this and then goes there, and another, you know, this kind of thing. So there are many contributions, but the only one that we will need for this particular purpose is something that is going to correct this internal line over here, okay? We are not going to consider, if there was a line from here to here, then I don't know exactly why we don't consider that something for you to think about. This thing emitting and reabsorbing, etc., is just dressing the external lines, okay? And if you did something over here, that is just dressing the effective vertex over here, and that vertex actually correction leads to something else, which is the anomalous magnetic moment, which we will take up later, but for the moment we are interested in this. So the interesting loop diagram is this. Let's draw it like this. And what kind of diagram is this? For abuse of notation, this is called vacuum polarization, okay? It's an old name, historical name, so just stay with it. So then this thing here, the new diagram is going to be one where G mu nu is replaced by G mu nu by Q squared is replaced by G mu nu by Q squared minus I by Q to the 4 times another tensor I mu nu. Why Q to the 4? Why Q to the 4? Because there are two internal lines now, two propagators, each of them Q squared, okay? And this I mu nu is something that is associated with this, which we have to say what it is. So I mu nu is equal to minus GE squared integral d4k by 2 pi to the 4 times trace of gamma mu. What is this k over here? K, which momentum? It's the loop momentum that's circulating in here, okay? And you have to do an integral over all k because it's not fixed, except by momentum conservation, which is fixed at each of these vertices, otherwise it's free. So this is like in second order perturbation theory in quantum mechanics, you have a sum over all intermediate states. Here this is equivalent to a sum over all intermediate states. The intermediate states are virtual particles that can carry any momentum, right? So there's no restriction on that momentum, and that's the reason why You had to do an integral. Okay. K slash plus MC gamma nu, then K slash minus Q slash minus MC. What are these factors over here coming over here? What are these various factors? See, these two internal lines are propagators of Dirac particles, right? So those two propagators appear in the denominator downstairs, but we don't like to have Dirac propagators in the denominator. So what do? We rationalize them by multiplying upstairs and downstairs by the same thing. Then we use the properties of the Dirac matrices and turn them into something that look like propagators of scalar particles. But these things will have to stay here on top. So this is k squared minus m squared c squared times k minus q squared minus m squared c squared. Is it clear? Every single thing that I have just said over here, it's nothing very great. There's an integral over the loop. There's a propagator for each one of them. The propagators are k slash plus mc, k slash minus q slash plus mc downstairs. But we don't like them downstairs, so we multiply upstairs and downstairs by the same thing. And so that remains in the trace. Those two guys remain in the trace over here. And whatever was downstairs from Dirac algebra just become objects that look like propagators of scalar particles. Okay. Now these are all prereqs for this course that you're supposed to know this. Do you follow? Everybody follows this? Yeah. We haven't done that yet. That is all still sitting here in this space. In a sense, yes. Otherwise, it wouldn't have got replaced by this. Yes, that is done. Otherwise, you wouldn't have got this. That is done, and after that, this is what you get. Yeah, you're right. I mean, it's only after the sum of the spins that you get these things. But basically, everything is done. This after doing this, we have also done that. Okay. No. Wait. No, wrong. We don't do it. Here we are only talking about this internal part over here. You're talking about the sum of the spins and all for these external things. Okay. This is just the tensor associated with this part. Sorry, I'm sorry, I just got confused. Yeah, this is just coming from the property. Right? There are too many spinners over here, so I just got momentarily confused. Okay. Now look at this and you tell me how badly divergent is this, because there's an integral all the way from 0 to infinity. Okay. Now somebody have a look at this and you tell me what the naive degree of divergence of this particular object is. Okay. Here, take a chalk, go and estimate it for me. No, you just do it. Here, I'll give you a piece of chalk. No. K cube dk. You can't lose the dk. Okay. Keep it as k cube dk. Yeah. Yes. Right. So the total one is k to the 5. No. So it goes as k dk, right? Yeah. No. But write it properly. No. Write it as k dk. K dk. Yeah. So if you do an integral, then it goes as lambda squared. So now you put an integral over there. Write an integral. And 0 to lambda, not zeros we don't need, put a capital lambda on top. So now this goes as, and what kind of divergence is that? It has a name, no? It's not linear, it's not cubic. What is it? Exactly. So it's quadratically divergent. Okay. But it turns out that in practice, what really plays a role is not that badly divergent, but rather this I mu nu. Let us try to give it a decomposition in terms of the only vector we have in hand. What is the only vector we have in hand in this particular thing? As far as this is concerned, there's only one free vector. K is also a vector, but it's integrated over. What's the only vector that we have in hand over here? This Q, no? Each one of these is a vector. P1 is a vector, P2 is a 4 vector. Each one of these is a 4 vector. Q is a 4 vector. It's okay. So you can have two independent vectors, P1 minus P2 and P1 plus P2. We always have that choice. Okay? And this kind of thing you always do actually. Okay, so this I mu nu over here, what are the possibilities? It has two indices over here. So you give me a rank 2 tensor in mu and nu. Any rank 2 tensor you know in mu and nu? No, I'm not talking about gravity, just flat space. Okay. What about the metric tensor? G mu nu. Okay. So it will definitely have a piece that goes as I G mu nu. So I'm trying to decompose this. And then we have a Q, but we have already used up mu nu, then it can be only the norm of the vector Q squared times some function of Q squared. Not of Q, not of Q mu, but of Q squared. Okay. So this means that there's one invariant that we can associate with Q, which is Q squared. Okay. That's the norm of that vector plus Q mu, Q nu times some other thing which is called J of Q squared. Okay. So this is a decomposition of this I mu nu. This is the only possibility with the objects we have in hand, which are the metric tensor and the vector Q mu. Okay, fine. You could, no problem. But we are just keeping it explicitly just for sake of dimensions, actually. Yeah, exactly. We want to keep it balanced. Now I'm going to ask you to convince me, or at least convince yourself, that the second term will not play any role. Why is it that it will not play any role? When we eventually calculate everything, there we will do what you're asking us to do, is when we eventually calculate the square of the matrix element, and then we have all these particles and so on, etc. After you do all that, this thing will not play any role. Why? Now recall that this Q mu is P1 minus P2, and that P1 and P2, they will act on what? P1 and P2 will act on this, and it will act on this. Okay, then they will satisfy the Dirac equation, and then they will drop out. So this will not contribute to the square of the matrix element. This kind of thing is always done in your QFT courses. You must have calculated many processes where you always subtly use the Dirac equation to get rid of some terms, not contribute to the square of the matrix element. Because of Dirac equation. Okay. But when you have things like this, propagators and all like this, what is it that you do in order to actually study something like this? When you get two propagators in the denominator or three propagators in the denominator, and you have to perform this loop integral, what do you have to do when you have products of propagators? Mr. Suresh, no idea? You did QFT1 or not? Okay. Whenever you see propagators or a string of propagators, 2, 3, 4, 5, then you combine the propagators. Okay, so that's why I was leading you up. When you have propagators, plural, you have just one propagator, nothing to do. You can just integrate over this. And that's an example of a tadpole diagram where you don't have to do anything. Okay, a tadpole, nothing has to be done, just integrate. But if you have two propagators, you have to combine them. How do you combine them? How do you combine propagators? Now I'm going to keep asking you, and I'm not going to do it for you because you're supposed to have done it. So at least I'll tell you the keywords. You have to learn on your own if you haven't done it. Okay. All this is there in Romao. If you sit down with his notebooks, you will see that he has done all of them. So it's up to you to take the trouble to download them, run them, read what he has done, what he has in his documentation, then you learn. Okay? The way I learned it is the way you also have to learn it. Yeah. Your name? I'm sorry, I still don't remember you. Aman. Okay. You are, of course, Kirana. You're the guy who beat me yesterday. How could I possibly lose that queen? Because my mind is not working. Okay, tell me, how do you combine these? By now you have to know what it is. You have to use the Feynman parametrization to combine denominators. The Feynman parametrization is the trick within quotes. You have to combine them using Feynman parameters. If you have two propagators, how many parameters will you need? You will actually need two, but there's a delta function constraint on them, so you'll need only one. Okay? If you have three propagators, how many will you need? You'll need three, there's a delta function constraint. So there'll be two independent Feynman parameters. If you have n such propagators, you'll have n minus 1 independent Feynman parameters. Okay? So after you combine them, then you can do the D4 integral. Okay? Do D4 integral you can perform, and what remains is the integration over the Feynman parameter. That is yet to be done. Okay? So after combining and doing D4k integral, the answer is I of q squared is GE squared by 12 pi squared times a piece that looks like this, dz by z, from m squared to infinity. So this is a kind of a Feynman parameter. Okay, there are different kinds of Feynman parameters. Sorry, this must be, wait a minute. Okay, fine. Times a piece that looks like this. Actually, this is not the Feynman parameter, but for the moment we will keep it like that. Use the same thing. This Feynman parameter is integrated from 0 to 1, z times 1 minus z times logarithm of, this is a very typical expression, minus q squared by m squared c squared times z minus 1. I guess I should close this brace like that. So there are two aspects to this. One is a piece that looks like it is divergent. Okay. Now that's not surprising because we knew that this thing was divergent in the first place. But we said that we carried out this decomposition. There's a part of this decomposition which will not contribute to the square of the matrix element because of the Dirac equation. and there's a piece which survives, which we have to evaluate. But the nice thing about whatever has survived is that it's not quadratically divergent, but it's only logarithmically divergent. Okay, this is how it is. Okay, there's no secret or there's no subtle meaning and all that. Just so happens that what you thought would be a quadratically divergent piece actually is much less divergent. It's only log divergent, and that's what it looks like. So the first term here, I don't call it Feynman parameter, here I call it a Feynman parameter. So the first term is something, and what are we going to do with this thing? M dz by z, let me call it z, m squared is goes as logarithm of m squared by m squared. So I introduce what is called a cutoff. And this divergent piece, please note, does not depend on q squared. Okay? It's only this finite piece which is depending on q squared. Yeah. No, that has a reverse divergence, but anyway, it doesn't contribute. Now I'm going to go and get myself a bottle of water while you people calculate this on Mathematica, with including the -6. So without the -6, I will call this f of minus q squared by m squared c squared. Don't call it q m squared c squared, call this x. And evaluate this on Mathematica while I go and get myself a bottle of water. You can also use assumptions that x is real. Okay, when you're doing this integration, use the assumption that x is. You don't have Mathematica? Share with somebody. No? Whoever has Mathematica, please share with everybody. You're the only one. Anybody else with Mathematica? So everybody now depends on Leo. So oh, look at me, how silly walking with this thing. You don't integrate the x. No, no, you have done it twice. Only one. No, you have the result. Yeah, can you please write it down? I don't know why it says yeah. Yeah, yeah, it's fine. Yeah, this answer is great. The only thing is I don't know why it says for x smaller than 4. Then we need the analytic continuation of that. Just remove the error. No, or greater than 4. It's 34. Yes. Yeah. Okay, right, no problem. Fine. The numerical value. Let's remove the minus sign. So, yeah, call this here. Yeah, we don't need the. Okay, so I'm going to ask you to. It's okay. No, no. So now, these some numerical values. Make a table. For x 0.1, 0.01, 0.001. So let's see. So he gets an expression which is basically what I also have, minus 5 by 3 plus 4 by x without the minus sign, 2 times x minus 2 by x times square root of x plus 4 by x tan h inverse of square root of x by x plus 4. Okay, so this is our f of x, right? So let's make a table. X f of x 0.1, 0.05, 0.01. Let's see what it gives. Zero point zero zero. Really? Yeah. Yeah. I prefer that because I know what it's supposed to be. 0.02. Then 0.1. Then here 0.0. Yeah. So for small x, what is it going like? So f of x goes as, have a look. What's the factor between these two? This and this? Yeah. Yeah. So f of x goes as x by 5 for x much less than 1. Okay. Now let's look at 10, 100 and 1000. See, I can write down the formula, but unless you actually calculate it for some values, it won't stick in your mind, no? So that's the reason for doing this. 10. So that's the thing. So I don't know why it does that. You need the analytic continuation of that arctan. So I didn't have this problem with my version of Mathematica. So you just give x as reals rather than as x greater than 1. Oh. Hmm? Yeah. Yes. Yeah, so that's why I'm saying you need an analytic continuation of this. So you just give it x greater than 4 and let's see what it gives.
I'm trying to retry it with the elementaries with octopus.
Yes, yeah, yeah.
Slow, so maybe we just have to wait.
Yeah, no, it comes. I've done it. Yeah. But what do you expect it would be? Take a look at this thing and tell me what do you expect that it would be? Which is the piece that you think would start to dominate? It would be this thing, no? The inverse of the hyperbolic tangent. So what kind of a function is that? The inverse of the hyperbolic. It should be a logarithm, right? It should be a logarithm of this argument. That's what you expected it ought to be, right? Yes. So that is why I'm asking you to do it for 10, 100 and 1000, because let's see if it goes, if this is double this and this is 3 times this. So that's the reason why I gave it. You can just put x equals 10 in your integral and then evaluate it. See what you get. But you may be right. Then we may have to take minus 10 minus 100. I don't know what it means. Did it come out? Anyway, let's forget it and you just say that this goes as log x for x greater than much greater than 1. Okay. No, it doesn't make sense. Okay, so in the book of Griffiths, he says that there's a particular choice. He said that, okay, so then what does he say? What's the next thing he says? So he says that, look, your I of q squared is then equal to ge squared by 12 pi squared, 12 pi squared times logarithm of m squared by m squared minus f of minus q squared by m squared c squared, like this. Okay, so this is the simple calculation that we have done, and nobody can have any quarrel with this. It's just a simple loop integral that we have done. We have not done any interpretation of anything that's right or wrong. So what needs to be done? Since you people have done quantum field theory, you should have some idea of what is going on. In a collision like this, in a collision like this, q squared is minus 4 absolute p squared times sine squared theta by 2 in the center of mass frame. This you all know, that elementary kinematics tells you that this has to be the case. We have not done anything complicated so far. Okay. So actually what this amounts to doing is to take minus ge squared in the matrix element. This amounts to taking minus ge squared bunch of u bars g mu nu by q squared, and then this whole blob is now replaced by 1 minus ge squared divided by 12 pi squared times logarithm of m squared by m squared minus f of minus q squared by m squared c squared times again the bunch of spinners like this. But then this looks absurd, that the matrix element has become something that is divergent. So what to do about this? What shall we do about this fact that this thing has become divergent and looks not so good? There should be closing this bracket here also. What shall we do about this? Now, you people have done courses on field theory. You have done renormalization, you've written papers, exams, you've got A grades and A plus and so on. Okay? So, you people really should have taken this next year. But anyway, since I'm doing things quite slowly, you can say that, okay, you have already learned this. What should we do? We shall redefine this charge. Okay? We will say that this charge here actually is not an observable thing, but the charge, so-called charge that we have over here is not really the charge, but it has to be redone in such a way so as to absorb this apparent divergence into a redefinition of the charge. Okay, so that is what is allowed. If the theory is renormalizable, then you're allowed to do it. So then let us absorb the divergent phi piece. With a redefinition of the charge and write GR as equal to GE times square root of 1 minus GE squared by 12 pi squared times logarithm of n squared. It seems like something unnatural that we have to do, but there's nothing unnatural. The point is that if it was that you have a free Lagrangian and you had no interactions, then from an epistemological point of view, you can't do any measurement anyway. If there are no interactions, there's no question of doing any measurement, okay, or any scattering or anything, okay. So what we had called GE, which is just something in the Lagrangian, is something that remains unobservable until you actually do an experiment, which is a scattering experiment of this kind. And in the process of doing this, we ran into all this, and then we say, that parameter that I introduced was itself divergent, and this induced divergence is reabsorbed into that to give a finite coupling constant that makes sense. Okay, that's really how it works. There is no mystery, magic, nothing. So if you have now done this reabsorption of this infinity into a redefinition of the charge, then you have a perfectly finite matrix element, but with a correction that is of order g to the 4. So we end up with a perfectly well defined matrix element now. So this is perfectly well defined, minus GR squared. Why do we give this name R over here? R for, right, U bar P3 gamma mu U of P1 G mu nu by Q squared times 1 plus GR squared by 12 pi squared. Now we are calling this GR squared without any loss of information, because it looks like it should have been GE squared, but this is GR squared because it does not involve any higher order contributions compared to this. So you can replace GE by GR in this term. You can't do it here, but you can do it here. This is the one thing that will take a little bit of understanding why it is the case. Times therefore q squared by n squared c squared. Okay, that's how it is, whether we like it or not. So this is how I write it. So infinities are gone now, no infinities. Perfectly finite, except that what was a coupling constant is not a constant, but is something that varies as a function of the momentum that is carried by the internal line. Okay, so this is the origin of what is called a running coupling constant in quantum field theory. So this is running coupling constant in field theory. Okay, and it is showing up in this particular way over here. So in this example, gr squared, which is a function now of q squared because it is running, it is gr squared at some 0 times 1 plus gr squared at 0 divided by 12 pi squared times f of minus q squared by m squared c squared. Now Griffiths says, how is it that if this was the case, nobody noticed this until the 1950s or so? How come Rutherford didn't notice all this? That's because this variation is very slow, and he considers a case where this q, or rather the velocity, is taken to be c by 10, and he says that the correction is of the order of 6 times 10 to the minus 6. Okay, now I want you to estimate this from the formula that we have. Okay, that we have this particular correction. Now I can actually rewrite this not for gr squared, but I'll write it for alpha. Alpha of q squared is alpha at 0 times 1 plus alpha at 0 by 3 pi times f minus q squared by m squared c squared. Close this. Okay, so I want you to get this number for me where he gets this 6 times 10 to the minus 6. Use all the formulas on the blackboard. Use this formula and use this formula and get me that particular number. And we said that f of x goes as x by 5 for x. Shall I do it for you? I can write it for you. Alpha at 0 is alpha at 0 1 by 137, right? So 1 by 137 times 1 by 3 pi. Then it is c by 10. So see, if it is c by 10, you get 1 by 100. 1 by 100, you agree? If it is c by 10, if the velocity is c by 10, q squared is 1 by 100, but there's a factor 4 sitting over here. So you have 4 times 100 divided by 5. Now somebody please calculate this for me. I've also done it somewhere. No, this is not correct. Yeah, exactly. So where exactly is the problem? Alpha by 3 pi squared center of mass strain. I had just done it the other day. Now I can't find it. By 3 pi. Yeah, thanks. Yes. That's much better. Thank you. Yeah. So we lost 4 orders of magnitude. Yeah. 6.16 or something like that it gets, right? 6.2 times 10 to the minus 6. See, because of this course preparation, I'm like busy all the time because I like to check every single number before I come, going totally insane. Yeah. Do you like this formula over here? I mean, it's not a matter of like or not, but have you seen something similar? I'm going to lead you up to a very nice result slowly, starting with this thing. Okay. So let us now consider, asymptotically what happens. So what can I do with that particular expression? I write it as 1 by, so alpha of 0, so alpha at q squared is alpha at 0 times logarithm of q squared divided by m squared c squared, right? When q squared is large, q squared is have you seen something like this anywhere in any of your courses? Some of you say you haven't done QFT or QFT1, QFT2. You have come across renormalization group equations. One loop RGE. Give me any example of one loop RGE that you have seen in any course. What about lambda 5 to the 4? Lambda 5 to the 4 theory. So this is plus s going to t and s going to u. You must have come across this, no? Now, if you people don't respond to any of my questions, how can I proceed? Have you people done one loop RGE or not? Then how can I teach you all these things? You shouldn't have taken this course. You should have taken it next semester. I'm sure Leo's done it, but you've probably forgotten some time ago. Yeah. So it's the renormalization group equation that controls the flow of coupling constants. Okay, and the so-called beta function by definition is mu dg by d mu, where mu is the scale parameter, or mu is the momentum. So in general, it's a partial derivative, but for the present, we'll just take it as an ODE, dE by d mu. Okay, and I'm going to give you the beta function for QED. For beta function for QED, I'm going to tell you is e cubed by 12 pi cubed, and this comes from usual consideration of the three diagrams: vacuum polarization, self energy, and the vertex. Okay, so that gives rise to this. I'm going to ask you to integrate this equation and give me the answer that relates. So alpha by definition is e squared by 4 pi at a particular scale q squared, I want you to integrate this and give me a result for alpha at q squared in terms of alpha at q squared equal to 0. Okay. Now one of you has to come and do this on the blackboard. Don't think of this as particle physics field theory. Think of this as a problem in your math methods course where you're integrating a first order differential equation. Okay, nothing more. Okay, I need a volunteer. Anybody can come and do it. Yeah, does Dhruva want to do it? Yeah, come, just do it. Yeah, just plug it in, do the integration, because I want to relate it to this answer that I have, which we did explicitly today I want to know how this is related to this. Hmm? That's right, that one. Yeah.
Sorry.
You better wear it because we are going to record it. Should I be the only one who's being recorded? Very good.
Uh, don't you have to do the beta is
Why BT by G?
what? Okay, G was the subs. Okay.
BG, not partial.
Yeah.
So integral of dg by, you have to write it,
Beta.
no? G is
Okay.
G, right?
Beta is just constant. Okay.
No, it's not. DE. G is a generic coupling constant here.
Okay. 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 Now I get it.
Very good. Sorry, here it should be 5.
Something like this. Value of mean.
So this is the indefinite integral. Now you are going to integrate this on the left hand side from the scale mu1 to mu2. The right hand side, the limits of integration are such that
Okay.
at the scale mu1, it has the value alpha mu1 and scale mu2, not alpha, but let's say it is to be evaluated at the scale minus at that scale.
Okay.
So you have to, now E is also carrying an argument.
Mm.
So E mu2 minus E.
Okay. Okay. Fine.
Will become pi squared. Sorry, it's
Okay.
it's correct, pi squared. There also. So yeah, thanks. So now I'm going to get the final answer, which is, and it's written in a very particular way. It's written in this way. It's written as alpha at the scale at mu1 is alpha at the scale mu naught divided by 1 minus alpha at the scale mu naught divided by 3 pi. 3 pi times logarithm of, here we write it as a square. These are all the things that you have to know. This algebra that you have to know, and then you have to realize that it is written in this particular way. Okay, in this particular way, it's written. But here you see this alpha at mu1 is related to alpha at mu naught but this extra factor is appearing in the denominator. Whereas in what we got over here, it is in the numerator. Okay. So what to do about that? It looks similar, but it's not yet the same. So what is the resolution of this particular thing? It is the same, or it ought to be the same, and it's not. So what is the actual physical meaning of this particular thing? This means that when this electron is scattering of the muon, they don't see their actual charges, but they are only seeing part of the charges because it is getting screened by the virtual E plus E minus pair that is produced in the vacuum. Okay, so this is the effect of the screening. Okay, and this is the effect only of the screening once. So this is the effect of getting screened once. But since you are such clever boys and girls, you'll say, how do I know that this is the only diagram? What about a further screening, that this virtual photon doesn't see this charge and maybe it sees only part of that charge? Okay, so it gets screened again. But what is to stop us from doing this again and again? Maybe it gets screened 3 times. And how many such times can it get screened? It can get screened an infinite number of times. Okay, so if it gets an infinite number of times, it gets screened like this. And the first time it gets screened is a term like this. The next time it gets screened, it's a square of this term. Then it's a cube of this term, etc., etc. What kind of a series is that? It's a geometric series. And if it's a geometric series, you know, with an object or a ratio that is smaller than 1, what can you do with such a geometric series? You can sum it. And when you sum this, what do you get? This thing, which is exactly what you have over here. Okay, so you see how nice it is that by starting with a simple equation like this and a simple process like this, we were able to do some of this funny algebra, and then we were able to reabsorb this infinity, etc., etc. Then we use these heuristic arguments of this kind to show that there is an effective screening of the charge, but it is not screened in an arbitrary way, but it is screened in a controlled way, which leads to a basic evolution of the coupling constant, which is governed by the renormalization group flow of this particular coupling constant. And how do we know that this is the correct beta function? Well, for this you have to do the one loop calculations of each of these diagrams, which you can do from the notebooks that Romao has given you. You can calculate the renormalization constants Z1, Z2, Z3. You can plug it into the expression for the beta function, and you can find that this is the answer. Okay, but this is a simple way in which we have got everything right. We have even got the factors of 3 pi and everything right, starting with some simple considerations. Of course, we didn't do the d to the 4 integral and all that, but after all, we have to take something for granted, no? So we have taken that for granted, and we've got a result of this kind. So this is where I'm going to stop today, and then let's discuss some more questions. If you have, let me know. We can discuss. We still have about 7 or 8 minutes in the class. I know it's a bit heavy going, but it can't be helped. Is this the only kind of screening that is possible, or something else can happen? This is the kind of screening that happens in a theory like QED, you know, which is an abelian gauge theory, where this beta function happens to be positive. There's one more thing that you guys forgot to ask me. What is it that tells you that you can only have an E plus E minus pair in the over here? You can also have a mu plus mu minus pair, no? The energy is sufficient. So you will get a contribution from each one of the particles over here, provided this Q squared energy is large enough. Okay. In this example that we did with that 6 times 10 to the minus 6, of course, at that energy, you care only about E plus E minus pairs. You don't look at, maybe, I don't think mu plus mu minus is needed at that energy. So this beta function over here has this positive sign. If you did it in scalar QED, what is meant by scalar QED? Where the charged particle is a Lorentz scalar. Also, this beta function is positive. I think the factor is different. I think it is 48 instead of 12. but it's still positive. So there are some theories which are needed in order to have a beta function with a negative sign, in order to explain the strong interactions. And what is the candidate for such a theory where the beta function may be negative? That candidate is non-abelian gauge theories. Okay, so that is how you arrive at non-abelian gauge theories, as the only possibility where you can have this property where the beta function is negative, and such theories are called asymptotically free. So this means that in a theory like QED, as the momentum increases, the coupling constant increases, whereas in asymptotically free theories, as the energy increases, coupling constants decrease, and only non-abelian theories, gauge theories, are the only candidates where such a thing can happen. Okay, so the beta function, all this behavior, everything is analogous except the actual value of the beta function in non-abelian gauge theories is what it is. Okay, it's not this, but it is something that appears with a negative sign. So there, I think what the vacuum is doing is it is anti-screening the charge, whereas here the charge is being screened. So this is the main difference between the two. Okay, and yeah. Yeah. Yeah, you could do all those things, but the question is what is going to contribute to something like this. Okay, this is a heuristic argument. Now that kind of thing, first of all, it's a higher loop diagram. So this is also in a sense two loop, but it's a fake two loop diagram because actually this is one particle reducible. If you cut this is still a valid diagram. Okay, so that is why in renormalization theory, the role of one particle irreducible diagrams is very important. So you have to go into the theory, say what exactly something makes sense or not. It's all context dependent. Of course, such diagrams are there, but is it relevant for this discussion? Any more? Okay, so if there are no other questions, I think I can stop here.